Hello everyone, and welcome to this detailed walkthrough of CFD numerical problem. In this lecture, we are going to analyze the one-dimensional steady convection diffusion equation. Now, this equation, as represented over here, is very fundamental in CFD because it combines two physical effects. One is the advection, which represents the transport of a scalar phi by a flow with velocity u. And the second one is the diffusion, which represents the spreading of phi due to a gradient, which is controlled by the coefficient, which I would be saying as half t. Now both this u and half t are positive constants here, so we have a simple but very instructive model over here. Our goal is to discretize this equation using the finite differences on a uniform grid, then understand the errors we introduce, and finally extend to the unsteady case to examine the stability. We will use the central differences for both derivatives because they are second order accurate, but as we will see that choice comes with some interesting consequences. Now, we discretize the domain into a set of points or nodes equally spaced by delta x. At a generic interior node I, we need to approximate the first and the second derivatives of phi. The central difference for the first derivative takes the value at the two neighboring nodes, subtracts the left from the right, and divides by twice the spacing. Intuitively, this gives an approximation to the slope at the center because the line through the 2 points has a slope that approximates the tangent at the midpoint. Similarly, the central difference for the second derivative uses the 3 points. It's the difference between the forward and the backward first differences divided by delta x, which essentially gives an approximation to the curvature. So we substitute these approximations directly into the partial differential equation and we can get the finite difference equation as displayed over here. So this is an algebraic equation that relates the unknown phi values at three nodes. So for the whole grid, we will have a system of such equations which we could solve. But before we solve it, we need to understand how accurate this approximation is. Now moving on to find the truncation error and to find out the order of accuracy, we go back to the calculus. We assume that phi is a smooth function that satisfies the exact partial differential equation. Then we insert that exact phi into the finite difference formulas and see what remains. This remainder is the truncation error. It tells us how much the discretization deviates from the original equation. We would be expanding the phi at I plus 1 and I minus 1 in the Taylor series about point I. The Taylor series is an infinite sum of the derivatives multiplied by the powers of delta x actually. I will write them out explicitly as being displayed on this particular slide as phi I plus 1 and phi I minus 1 is being expanded using the Taylor series expansion approach over here. So these are represented by the equations 2 and 3 respectively. Now, when we form the central difference for the first derivative, we subtract the phi I minus 1 from the phi I plus 1 and divide by 2 delta x. Notice that the even order terms cancel out and the odd order terms add up. So we get the final relationship in the form of this particular equation number 4 as phi I plus 1 minus phi I minus 1 divided by 2 delta x equals to the equation as being displayed in this equation 4. So the leading term, a leading error term is of the order of delta x whole square, which is why this is called a second order approximation. Similarly, for the second derivative, we add the phi I plus 1 and phi I minus 1 and subtract 2 phi I divided by the delta x whole square. So this time the odd derivatives cancel out and the even one remains. So it can be seen from this particular equation number 5, and we can again see that the leading error is of the order of delta x whole square. So now we plug these expansions into our finite difference equation. On the left hand side, we have u times the first derivative expansion. On the right, we have the coefficient times the second derivative expansion. So if we bring everything to one side, we would get the final relationship in form of this equation 6. But the exact PDE says that the first two terms sum to 0. Therefore, the remaining terms constitute the truncation error, which I have represented over here by the term tau. So tau would be equal to u times delta x square divided by 6, third derivative of the phi at node I, minus half t, which is the coefficient, delta x square divided by 12, fourth derivative of the phi at the node I, plus of higher order terms of the fourth order accuracy, fourth order. Now, the smallest power of delta x in this truncation error is delta x whole square. So the scheme, we would say that the scheme is second order accurate. This means that if we have the grid spacing, the truncation error decreases by a factor of 4, at least asymptotically. Now, moving on to the modified equation, now we take a step further. The truncation error tells us how much the discrete equation differs from the original PDE. But we can also ask what PDE does the numerical solution actually satisfy? So this is called as the modified equation. It includes the leading error terms and gives insight into how the discretization behaves. For instance, whether it introduced the artificial diffusion or dispersion. So we will start from the equation as written over here, that u phi x minus the coefficient times the second derivative of the phi equals to the equation of the on the right as being displayed. Now the right hand side involves the third and the fourth derivatives. But we can simply simplify these using the original PDEs to express the higher derivatives in terms of the lower ones. So the idea is that the numerical solution will approximately satisfy the original equation. So we can use the relation u psi of x equals to the coefficient times the second derivative of the phi with respect to x. So to replace the derivatives. Now the first step over here is to differentiate the exact equation with respect to the x, which would give us the final relationship as psi subscript triple x equals to u over coefficient times the second derivative of psi with respect to x. Now, if we differentiate again, we would get the further relationship as psi 4 time in the subscript. It must be equal to u square over the coefficient square times the psi double derivative in the x direction. Now we substitute these into the truncation error terms, take the combination, we can get the final relationship as this equation being displayed over here. So the first term becomes minus u square delta x square divided by 6 times the half t times the double derivative of psi with respect to the x. So the second term becomes positive u square delta x square divided by 12 times the coefficient times the second derivative of psi in the x. So adding them gives the term minus u square delta x square divided by 12 times the coefficient times the second derivative of psi with respect to x. So the modified equation becomes very simplified as u psi subscript x minus the coefficient times the psi double x in the subscript must be equal to minus u square delta x square divided by 12 times the coefficient times the second derivative of psi in the x. So we can rearrange this to find the ultimate equation. So what does this mean actually? The numerical solution now behaves as it satisfies a convection diffusion equation with an effective diffusion coefficient, which we can represent over here as half t and effective in the subscript must be equal to the half t minus u square delta x square divided by 12 times half t. So since this correction term is negative, assuming u is greater than 0 and the coefficient is also greater than 0. So the effective diffusion is smaller than the physical diffusion. This is the leading error effect. The central difference scheme introduces a negative diffusion error which tends to steepen the gradients. But wait, this is very interesting over here that usually we think of the numerical diffusion as adding extra diffusion, but there is a sign which is opposite because we use the central differences for both the terms. However, this analysis is only valid when the error is small compared to the physical diffusion. So if this coefficient half t is very small, the modified equation's coefficient might even become negative, indicating that the numerical scheme becomes unstable. So we will see that later that this is connected to the grid Péclet number. Now, uh, the second part of this particular problem is about the numerical diffusion or dispersion. So in its first subpart, we have to identify the leading error. So from the modified equation saw, we just derived, we see the leading error term is a second derivative term, which was minus u square delta x square divided by 12 times the coefficient and whole multiply by the second derivative of 5 with respect to x. So this is an even derivative. In the wave propagation, even derivatives are associated with dissipation, smoothing, while the odd derivatives causes the dispersion, which are linked with the oscillations. So in our case, this even derivative modifies the diffusion coefficient. Even though the sign must seem to reduce the diffusion, it still represents a diffusive effect because it's a second order term. So the central difference scheme introduces a form of numerical diffusion over here, or more precisely, it alters the effective diffusion. In many practical problems where the physical diffusion is very small, this can lead to non-physical steepening or and even instability, which is why upwind schemes are often used for convection dominated flows. Now, the second subpart of this particular numerical diffusion and dispersion is about the condition for exactness. So the truncation error vanishes if the coefficient of the leading term is 0. That is, if we equate the equation u square delta x square divided by 12 times the coefficient half t. If we equate this particular term equals to 0. So for the non-zero u and the coefficient half t, this only occurs in the limit delta x when it approaches to 0. So if we consider the grid Péclet number, which is given in the numerical problem statement, Péclet number PE in the subscript is delta equals to u delta x divided by the coefficient. So the leading error is proportional to the Péclet number square. So for the scheme to be exact, we need Péclet number equal to 0. In practice, for a finite grid, the scheme will have some error. In fact, If Péclet number is large, which also shows that the convection dominates over there, the effective diffusion coefficient can become negative, which is a sign that the scheme is not monotone and may produce oscillatory solutions. So that's why for convection dominated problems, we often use upwind schemes or other stabilizations. Now, moving on to the part 3, which is about the stability of the unsteady equation. Here in this subpart A, we have to see about the explicit Euler with central differences. So now we extend our analysis to the unsteady case. So this particular equation being displayed over here is representing the unsteady case as partial phi over partial of t plus u partial phi over partial of x equals to the coefficient half t times second derivative of phi with respect to x. So we discretize the time with the explicit Euler method, which is the simplest time marching scheme. The time derivative is approximated by a forward difference, and we keep the same central differences for the spatial derivatives, but now evaluated at the old time level n. This gives us an explicit formula for phi at the new time level n plus 1 in terms of the values at the level n. So if we can see from this particular equation, we have the representation in terms of the finite difference, which is the phi I n plus 1 minus phi I n divided by delta t plus u times this phi I plus 1 in the superscript is n minus phi I minus 1 n divided by 2 delta x. So now we have to solve for the phi in the advanced time n plus 1. So if we rearrange this, so this is the finite difference equation. We will analyze it this for the stability. So in the part B and C, we are now on the von Neumann stability analysis. Now we perform a von Neumann stability analysis on this particular equation. So the idea is to assume a solution in form of a Fourier mode, which is phi I raised to the power n equals to g raised to the power n e superscript I beta I, where beta equals to k times delta x is the dimensionless wave number and g is representing the complex amplification factor. So the stability condition is when the modulus of this g would be less than equal to 1 for all betas. Now substitute this mode into the explicit finite difference equation. The terms becomes as listed over here, which is phi I raised to the power n gives uh, gn ei beta I, phi I plus 1 raised to the power n, and phi I minus 1 raised to the power n as displayed over here in form of the amplification factor and the dimensionless wave number. So plug these in and factor out the g raised to the power n ei beta I. So the factor g appears on the left as displayed over here in form of the equation. So now use the Euler formulas. The second term becomes simplified, and the third terms also becomes more compact. So now defining the Courant number from here, we can say that C equals to U times delta T divided by delta of X, and the diffusion number uh, can be represented equal to the coefficient times delta T divided by delta X square. So then G would be equal to 1 minus iota C sine beta minus 4D sine square beta divided by 2. So this is a complex number and its magnitude squared is must be less than equal to 1 for all beta if we have to satisfy the stability condition. Now uh, let us assume that S equals to sine square beta by 2, which ranges from 0 to 1. Then sine square beta must be equal to 4s times 1 minus s. And if we solve it, we expand this particular equation and we group the similar terms, and we can see that this particular equation is quadratic in s. The constant term is 1, so we need the extra part to be less than equal to 0 for all s in the range of 0 and 1. So consider the endpoints that at s is equal to 0, the modulus of the uh, g squared equals to 1, which means it is neutral. But when s is equal to 1, which implies that the modulus of g squared must be equal to 1 plus 4c square minus 8d plus 16d square minus 4c square. This particular equation must be less than equal to 1. So this gives us that 0 must be less than equal to d must be less than equal to half. So the first stability condition is that the d must be less than half in number. Now, the interior part is that the quadratic has the coefficient 16d square minus 4c square, as you have already noticed for s square. So if this is positive, the parabola opens upward, and the maximum may occur at any interior point if the vertex lies in 0, 0 and 1. So to ensure no overshoot, we also need the slope at s is equal to 0 to be non-parabolic. So we equate 4c square minus 8d must be less than equal to 0, which is c square is less than equal to 2d. Now this condition together with the earlier condition, the diffusion coefficient must be less than equal to half, guarantees that the quadratic is maximized at an endpoint, and thus the modulus of the g amplification factor squared must be less than equal to 1 for all values of s. So the stability conditions are very clear, which is the diffusion coefficient must be less than equal to half and c square must be less than equal to 2d. Now moving on to the interpretation part, we let us interpret these two conditions. The first one is that d must be less than equal to half, which is well-known stability limit for the explicit solution of the pure diffusion equation. It restricts the time step based on the grid spacing and the diffusion coefficient. Now, the second condition couples the advection and the diffusion. So for a given grid and given physical parameters, we can write it as u delta t divided by delta of x must be less than equal to under root of 2 half t delta t divided by delta x square. So squaring both sides of this particular equation, since both sides are positive to get the this particular form. So actually we keep it as c square must be less than equal to 2d. So this means that the Courant number squared cannot exceed twice the diffusion number. If the physical diffusion is very small, which means d is very small, then c must also be very small, meaning the time step must be very small, much smaller than the typical CFL limit for the pure advection scheme. So for the presence of the central differencing for the advection term over here combined with explicit time stepping forces a severe time step restriction when the flow is convection dominated. Now conversely, if the diffusion is large, D can be up to zero point 0.5 in value, then c square would be less than equal to 1, so c would be less than equal to 1, and that's the classical current limit condition CF, which is the CFL condition. So the stability condition essentially says for stability the time step must satisfy both a diffusion if limit and a more restrictive combined limit when advection is strong. Now, Summarizing and closing this particular lecture, we let us recap what we have learned in this lecture up till now. We started with the steady convection diffusion equation, discretized with the central differences, and found it to be second order accurate. By deriving a modified equation, we discovered that the leading error term is a second derivative that modifies the effective diffusion coefficient. So this is a form of numerical diffusion that depends on the grid Péclet number. Then we moved to the unsteady case and performed a von Neumann stability analysis for the explicit Euler central difference scheme. We derived two conditions. The diffusion number must be less than half in value, and the Courant number squared must be less than equal to twice the diffusion number. So these conditions show that when advection dominates, the time step must be severely restricted to maintain the stability. Understanding these error and stability properties is crucial in CFD. It tells us why the certain schemes are chosen for convection dominated flows, for example, the upwinding implicit methods, and how to select time steps safely. I hope this detailed walkthrough of a certain CFD problem has been very helpful and insightful. So if you have any questions, feel free to ask me. Thank you for watching and good luck with your next CFD lecture. Thank you.